Hi, everyone. Is this working? We're good? Cool. So I'm Keith. This is Yasmin, and we're part of an MIT team working towards recycling unrecyclable plastics. We're kind of focused around thermosets. So these are cross-linked plastic materials, and the reason we're interested in these is because these make up 18% of all the plastics that we produce globally. That makes up about 65 million tons a year, almost $500 billion in market value. And the reason we like looking at these is because less than 0.1% of these materials are actually recycled. Specifically, what we've developed is a molecular additive strategy that allows us to break down technically any thermoset material. We can do this by incorporating a small amount of additive, and this allows us to kind of break down these materials at low cost without sacrificing material performance, appearance, or manufacturing workflow. We have a few patents going on this, as well as some publications. And part of the motivation for this was because this plastic waste crisis that we're dealing with is getting increasingly worse. Our global plastic waste production is increasing at an exponential rate, and while a recycling of these plastics is also following exponentially, it's lagging far behind. And so what this means is that in order for us to actually catch up, we need to develop solutions for recycling plastic materials that can be applied to the materials that are actively being used today, rather than producing new materials at a whole that otherwise take very long to actually roll out. And the pictures actually look a lot worse than the graphs do. And so this is part of the motivation for us. Most of these plastics at the end of their life are being dumped in landfill, they're being burned, whether intentionally or not, or they're being dumped in the ocean or buried just out in the sand. This is a good picture actually, because that in the bottom right is a bulldozer for scale. And so this is a big problem. This is global and it's not going away anytime soon. And so we wanted to address this as chemists and as materials scientists. And in order to do that, we wanted to kind of take a step back and think about where we were. And so a lot of you might actually be thinking, well, most plastics are recyclable, and you'd be correct to think that. And in that sense, we're thinking about thermoplastics, which you can think about as long polymer chains, all hanging out together. They're held together by physical forces. And for that reason, they can be removed from one another. They can be melted, they can be dissolved, they can be reprocessed. And the reason those aren't recycled is largely systematic or sorting related, as many of us know. Thermosets, on the other hand, are distinguished by these small chemical bonds that tie each of these chains to at least two others. And so thermoset materials are holistically just a single molecule. And for that reason, they can't be remolded, they can't be melted, and they can't be dissolved. And broadly speaking, they're unrecyclable as a result.
And so some existing strategies do exist to circumvent these thermosets from going into landfills, but they're not really efficient. These things include pyrolysis, solvolysis, the introduction of exchangeable crosslinks, and thermodynamic recycling. The issue with these is they tend to be energy intensive, and beyond that, they're really material specific. And so you can't really generalize them, and it requires a lot of industrial involvement and a change to the workflow that's incorporated. So it's not easily adoptable by industrial partners. The scope is too limited with that, so we thought to ourselves, why not take a step back and ask ourselves, can we come up with something that is generalizable across different types of plastics that could be adopted by industrial partners? By surveying the literature, it seemed to us that most of these approaches included the introduction of a cleavable cross-linking moiety. And so basically, you would have something in between these different strands that you could cleave upon stimuli, and that would end up giving you a more malleable network, but it wasn't degraded, right? And so we, once again, decided, let's take a step back and ask ourselves, how can we ensure that we can, degrade this material, solubilize it, so that we can then reprocess it and remold it into something completely new? And we thought, if we move those cleavable crosslinks into the backbone of the material instead, then we can end up getting these degraded fragments. We're not going from starting material to polymer back to starting material, but we can at least remold it and introduce it back into new materials that take on new shapes and can be used for different applications. And so actually, we have found that these cleavable comonomer additives, as we've coined them, are actually incredibly effective at degrading these thermoset networks and then being reincorporated, these fragments being reincorporated into new materials without loss of the desired physical properties. And this is incredibly exciting for us because although we have a beachhead market of PDCPD, polydicyclopentadiene for any enthusiasts, it's actually a very generalizable approach and can be used in a number of applications, including things like tires, turbines, foams, automotives, and even in acrylics. So you can think of this as being used in anything that thermoset plastics are introduced into. And importantly, it includes multiple functionalities. So you have on-demand deconstruction that is specific to when you introduce the stimuli. You can recover the plastic and reuse it. You can also recover woven carbon fiber, which to our knowledge isn't done before using these chemical degradation approaches. And it is low cost and low loading of our additives. So it is more readily adoptable to industrial partners.
Yeah, and so with that, we propose basically that we can generate impact across scales with this technology. At the product level, we should be able to reduce material consumption while allowing for introduction of new functionality. For any commercial partners, we're able to let them innovate responsibly using our technology and in the long run help work towards their goals of reduced carbon footprints and long-term reduced costs. And globally, we think adoption of this technology in a widespread sense is going to help us reach that sort of circular economy that many of us are so interested in and kind of reduce the amount of waste generated and virgin material required for materials production. And so with that, we're chemists and material scientists. It pains us to not get to talk about the details. Please come through to the poster and we'd be happy to address that with you.